Hello everyone. In this video, I am discussing problems 20.7, last question of problem 20.7. Find the nature and location of the singularities of the following functions. There are 6 functions given to us. We want to find nature and the location of singularities of these functions. Given function f of z has z equal to a singularity. Singularity is z equal to a, then the singularity of f of z, we know that singularity is of 3 types. Singularities of 2 types, there are isolated and non-isolated singularities. Isolated means this is isolated, z equal to a is isolated singularity means its neighborhood doesn't contain any other singularities. But non-isolated means if z equal to a is singularity, its neighborhood has another singularity. It is non-isolated. This is isolated. That means neighborhood has no other singularities except a. So, a non-isolated is classified as removable, pole and essential. 3 types of singularities: removable, pole and essential. So, if z equal to a is a singularity of f of z, first of all we need to find the limit at a singularity. Limit at z equal to a f of z. When z is equal to a, what happened to the f of z? Finding the limit at z equal to a, if it gives a finite number. If it is a finite number, that means limit of f of z is exists at z equal to a and it is a finite number, then the singularity is removable. Then we said z equal to a is a removable singularity. If it is not exist finitely, that means z equal to a f of z. If we put z equal to a to the f of z or limit z tends to a f of z, we get infinity. That is not a finite number. If we get infinity or minus infinity, then it is a pole. Then z equal to a is said to be a pole. If neither removable or pole, then it is essential singularity. That means limit z tends to a f of z does not exist. If it does not exist, then z equal to a is essential singularity. So, we have removable, pole and essential. First we check the limit at z equal to a, the singularity z equal to a. If it is a finite number, then it is removable. If it is infinity, then it is a pole. If neither removable nor pole, that means limit does not exist, means it is essential singularity. Or we can find using the Lorentz series expansion. That is, if f of z has Lorentz series expansion, we know the Lorentz series expansion is, we have both principal and analytic part, but that means we have negative terms. If it is a minus 3, 1 by z minus a. If a is the singularity, z minus a whole cube. A minus 2, 1 by z minus a all square. And next term a minus 1, 1 by z minus a all raised to 1. And next term a naught, a1 into z minus a, a2 into z minus a all square plus a3 z minus a all cube, etc. These are positive powers and these are negative powers. Lorentz series expansion of f of z. Then, if all these negative coefficient of negative powers are 0, that means a minus 1, a minus 2, a minus 3, a minus 4, etc. all these equal to 0. That means in f of z we doesn't have these parts. All these terms are 0. If the coefficient is 0, then the terms become 0. So all the negative powers, coefficient of negative powers equal to 0, then z equal to a, the singularity z equal to a is removable. And next, if we have the term, first term a minus 1 not equal to 0, that means we have a minus 1 by z minus a in this term. All the positive terms are there, and a minus 2, a minus 3, all are equal to 0. That means we have in Lorentz series expansion of f of z, only a minus 1 is not equal to 0 if we consider the negative terms. A minus 1 is not equal to 0. All the a minus 2, a minus 3, all the higher powers are equal to 0. Then for the positive n, all the higher powers a minus 1 equal to 0. For n greater than 1. A minus 1 not equal to 0. Then z equal to a is simple pole. That means pole of order 1. If we have a minus 1 and a minus 2, a minus 2 not equal to 0, a minus 1 not equal to 0 and a minus 2 not equal to 0. All other powers a minus 3, a minus 4 etc. all are equal to 0. Then this is z equal to a is pole, again a pole of order 2. That means if the Lorentz series expansion contains one negative power, that means 1 by z minus a is there, then z equal to a is a simple pole. If it has 1 by z minus a and 1 by z minus a all square, then it is pole of order 2. All others are 0. That means generally if we have a minus k not equal to 0, up to a minus k, this is not equal to 0. That means k equal to 1, 2, 3, 4, k. Up to k, a minus k not equal to 0. And for k greater than, for n greater than k. That means a minus k plus 1, a minus k plus 2, all other terms equal to 0, up to k not equal to 0 and all other term equal to 0, then this is z equal to a is pole of order k. A minus 1, a minus 2, a minus 3 up to a minus k is not equal to 0, then this is pole of order k. Z equal to a is pole of order k. That means depending on the negative powers of z minus a, we can find the nature of singularity z equal to a. If it has no negative powers, then z equal to a is removable. And if it has one negative term, this is pole of order 1. And two negative term, that means negative power 1, z minus a power minus 1 and z minus a power minus 2. That is pole of order 2. And up to k is pole of order k. If it has infinitely many negative terms, that means a minus 1, a minus 2, all are not equal to 0. If a minus 1, a minus 2, a minus 1, a minus 2, a minus 3, this is not equal to 0, this is not equal to 0, this is not equal to 0. All the negative terms, infinitely many negative terms not equal to 0, then this is z equal to a is essential singularity. That means if f of z has essential singularity at z equal to a, the Lorentz series expansion of f of z has infinitely many terms of 1 by z minus a, 1 by z minus a square, 1 by z minus a cube. there are infinitely many terms of z minus negative powers of z minus a. Then z equal to a is essential singularity. So depending on the negative powers of z minus a in Lorentz series expansion, you can also find the nature of singularities. So let's move on to the questions. So our first question is f of z is equal to 1 by z into z2 minus z. So clearly we have singularities z is equal to 0 and z is equal to 2. These are singularities, and to find the nature of z equal to 0, singularity z equal to 0, let's find the limit. Limit z tends to 0, f of z. Limit z tends to 0, f of z is 1 by, if put z is equal to 0, we get 0 in the denominator. 1 by 0 is infinity. So this is limit z tends to 0, f of z, we get infinity. So this is pole. And it is simple pole. Also for z is equal to 2, limit z tends to 2, f of z equal to, again if we put z is equal to 2, this term becomes 0. So 0 into 2 is 0. So this is also infinity, this is pole. If you're finding the Lorentz series expansion, so let us consider the Lorentz series expansion of this function about z is equal to 0. That means 1 by z into 2 minus z, we can take 2 outside. This is 2z, means 1 minus z by 2. So that we can use the expansion of geometric series. That is, this is 1 by 1 minus z. So this is 1 by 2z is there, and 1 by 1 minus z by 2, we can use the expansion 1 plus z by 2 plus z by 2 square plus z by 2 cube. 1 by 1 minus z expansion when mod z less than 1 is 1 plus z square plus z cube, etc. So this is plus etc. and which is equal to 1 by 2z plus z by 2 into divided by 1 by 2z. That means z cancel. This is 1 by 4. And this is z square by 4 divided by 2z. 1z cancel. Z divided by 4 into 2. That means z by 8 plus this is z cube. Z square is there, and by 3 cube into 2 plus etc. And clearly only the coefficient of 1 by z is there. That means a minus 1 is not equal to 0. All a minus 2, a minus 3, etc. are equal to 0. Only the negative power is 1 by z. That means z raised to minus 1 is there. So this is z equal to 0 is simple pole. Similarly, we can find the Lorentz series expansion about z equal to 2 in a deleted neighborhood of z equal to 2. We can always define the Lorentz series expansion about z equal to 2 and z equal to 2 also a simple pole. Next function is f of z is equal to sine 1 by z. Clearly we can say that z is equal to 0 is singularity, and the limit z tends to 0 is z tends to 0, sine 1 by z is sine 1 by 0. This is does not exist. Sine 1 by 0 does not exist since it oscillates at z equal to 0. Function sine 1 by z equal to 0 oscillate at z equal to 0. So, z equal to 0 is clearly essential singularity. If you're finding the Lorentz series expansion of sine 1 by z, we know the expansion of sine z. Sine z is z minus z cube by 3 factorial plus z raised to 5 by 5 factorial minus z raised to 7 by 7 factorial, etc. This is the expansion of sine z. Sine z is an analytic function. This is Taylor series expansion. So, 1 by z, if you put z is equal to 1 by z, you get the Lorentz series expansion about z is equal to 0. This is about z is equal to 0. So, this is 1 by z minus 1 by z cube by 3 factorial plus 1 by z raised to 5 by 5 factorial minus 1 by z raised to 7 factorial plus etc. The power increases z raised to 9. So, here 1 by z raised to 9, 1 by z raised to 11, etc. So, notice that z equal to 0 is an essential singularity since it has infinitely many powers of negative powers of z. That means 1 by z cube, 1 by z raised to 5, 1 by z raised to 7. Now 1 by z raised to 9 is next term and 1 by z raised to 11, etc. So, infinitely many terms containing negative powers of z. So, z equal to 0 is essential singularity. Essential singularity. So, f of z has z equal to 0 as essential singularity. The next function is f of z is equal to tan 1 by z. F of z equal to tan 1 by z. Also, z equal to 0 is the singularity. It's clear that z equal to 0 is singularity. We can write it as, this is tan 1 by z. We can write it as sin 1 by z divided by cos 1 by z. Tan is sin by cos. So, this is sin 1 by z divided by cos 1 by z. What is the singularity? Clearly, z equal to 0 is a singularity. Also, it has singularity when cos 1 by z equal to 0. Denominator equal to 0. Cos 1 by z equal to 0. Cos function equal to 0. Cos z equal to 0 means z is equal to 2n plus 1 pi by 2. That means odd multiples of pi by 2 gives 0 for cos function. And even multiples of pi, n pi gives 0 for sin. Sin n pi equal to 0. Here we have cos z equal to 0, odd multiples of pi by 2. That means cos pi by 2 is 0, cos 3 pi by 2 is 0, etc. Odd multiples of pi by 2 gives 0 for cos function. So, this is 1 by z is 2n plus 1 pi by 2 for n belongs to z integers. What is z? Z is equal to reciprocal of this. Pi by 2 reciprocal is 2 by pi into 2n plus 1. So, this gives singularity for tan 1 by z. For z n belongs to integer. 2 by pi into 2n plus 1. And this singularity, this tends to, if we put n equal to infinity or n tends to infinity, this tends to 0. As n tends to infinity, then this is the singularity, limit point of, this is limit point of singularities. Limit point of singularities are essential singularity, and that is non-isolated essential singularity. Limit point of singularities are essential singularity. So z equal to 0 is an essential singularity. Limit point of limit point of singularities. These are singularities of f of z, and limit point of singularity is 0. Limit point of singularities are also a singularity, and it is essential singularity. That means we have singularity 2 by pi into 2n plus 1 and 0. These are singularities of tan 1 by z and are essential singularities. Z equal to 0 is also an essential singularity, and these singularity z is equal to 2 by pi into 2n plus 1 is 0 only for denominator. So we have singularities z is equal to 2 by pi into 2n plus 1. For n belongs to z, these are zeros of denominators for this function. So these are singularities. Also z equal to 0 is also a singularity, and it is limit point of these singularities. Limit point of singularities are essential singularity, and this is singularity when denominator equal to 0. That means these are poles. Or we can find using Lorentz series expansion. If tan z is equal to, we have the expansion of tan z, z plus z cube by 3 plus 2 by 15 z raised to 5 plus etc. This is the expansion of tan z about z equal to 0. Next term is 9 by 315 z raised to 7 plus etc. Now we finding the expansion of tan 1 by z. This is 1 by z. 1 by z cube 3 plus 2 by 15 1 by z raised to 5 plus 9 by 315 1 by z raised to, this is z raised to 7 plus etc. So for z equal to 0, this is expansion around z equal to 0. So z equal to 0 is essential clearly in the Lorentz series expansion. Clearly we have infinitely many terms of negative powers of z. So z equal to 0 is essential singularity. From the Lorentz series expansion we can say this. Or these are z equal to 0 is limit point of singularities of f of z. Limit point of singularities are always essential singularity. Z equal to 0 is essential singularity. And these are poles since this is 0 only for the denominator, not for the numerator. So 0 only for the denominator. So it will become poles of f of z, and 0 is the essential singularity. So two types of singularities. One is essential and others are poles and symbol poles. These are symbol poles. 2 by 1 n is equal to, for n is equal to 1 we have 2 by pi 3. 2 by 3 pi and 2 by 5 pi, 2 by 7 pi. These are symbol poles. Next function is f of z is equal to z cube minus 1, z square minus 1 divided by z minus 1 whole cube. Z square minus 1 divided by z minus 1 whole cube. Clearly z is equal to 1 is singularity. Z equal to 1 is our singularity. And when we finding the limit is z tends to 1 f of z, it gives 1 minus 1 0 divided by 1 minus 1 0. 0 by 0 form. Then use a L'Hospital rule, that means differentiate. Limit z tends to 1 f of z equal to limit z tends to 1, z is 1. Differentiate numerator, that is z square minus 1 derivative is 2z and denominator is z minus 1 all cube. Derivative is 3 into z minus 1 all square into 1. Now put z equal to 1, we get 2 by 0. Z equal to 1, 2 by 0, that is infinity. So this is pole. And how to find the order of pole? There is no need to find the Lorentz series expansion. It is easy to find the order of pole. Find the order of 0 of denominator and numerator. For the numerator, this is z square minus 1 is our numerator. For this numerator, z equal to 1 is 0 for the numerator. If we put z equal to 1, this becomes 0. Now, f of 1 equal to 0. Let it be f1. Numerator is f1 and for denominator let it be f2 z minus 1 all cube. f1 of 1 is 0. Now let's take the derivative. Derivative is 2z and what is 1 for derivative? This is 2 not equal to 0. So z equal to 1 is 0 of order 1 for numerator. Means first derivative is not equal to 0. So this is 0 of order 1. Now this is f2 of 1 also 0. Find the derivative f2 dash is 3 into z minus 1 whole square. Also f2 dash of 1 becomes 0. Now find f2 double dash, second derivative. Second derivative is 3 into 2z minus 1 all raised to 1. For f2 double dash of 1 also 0. Now find the fourth derivative. Sorry, third derivative, f2 triple dash. Triple dash is equal to 3 into 2. Derivative of z minus 1 is 1. 1 minus 0. So that is 1. That means 6 not equal to 0. So third derivative is not equal to 0. That means for denominator z equal to 1 is 0 of order 3. Third derivative is not equal to 0. And here z equal to 1 is 0 of order 1. First derivative itself not equal to 0. So order of the pole is 3 minus 1. Order of the denominator 3 minus order of the numerator 1, that is 2. Pole of order 2. Pole of order 2. So z is equal to 1 is pole of order 2. Next function f of z is equal to e raised to z divided by z minus 1 all power 4. Clearly z is equal to 1 is the singularity. Z is equal to 1 is singularity. And if we find the limit at z is equal to 1, limit z tends to 1, f of z is equal to e raised to 1 divided by denominator is 0. So this is infinity. So this is pole. Z is equal to 1 is a pole. And how to find the order? Let's check the numerator. Numerator e raised to, when we put z is equal to 1, e raised to 1 is, which is not equal to 0. That means z is equal to 1 is not a 0 of numerator. For the denominator it's itself 0, z is equal to 1 is 0. Finding the derivative, derivative is 4 into z minus 1 all cube. This is also 0 when z is equal to 1. And next derivative is 12, 4 into 3, 12 into z minus 1 all square. And this is also 0 for z is equal to 1. So this is first derivative, this is second derivative. Third derivative is 12 into 2, that means 24 into z minus 1 all power 1. Also 0 for z is equal to 1. Now fourth derivative is 24 itself. Z minus 1 derivative is 1, which is not equal to 0. So z is equal to 1 is pole of order 4. Since numerator z is equal to 1 is not a 0 of numerator. So z equal to 1 is pole of order 4. We can also use the Lorentz series expansion. This is e raised to z divided by z minus 1 all power 4. For z equal to 1, about z equal to 1, so make this is z minus 1 plus 1. Let's write z as z minus 1 plus 1. And denominator is z minus 1 all power 4. So this is e raised to z minus 1 into e raised to z minus 1 into e raised to 1 and z minus 1 all power 4. So e by z minus 1 all power 4, we have the expansion of e raised to z. What is e raised to z? Expansion of e raised to z is 1 plus z by 1 plus z plus z square by 2 factorial, z by 1 factorial, z square by 2 factorial, z cube by 3 factorial, etc. This is 1 plus z is z minus 1 plus z minus 1 all square by 2 factorial, z minus 1 all cube by 3 factorial plus etc. Now let's multiply with this z minus 1 all raised to 4. E is constant. So 1 by z minus 1 all raised to 4. 1 z minus 1 cancel. This is z minus 1 all cube plus 2 z minus 1 cancel. 1 by 2 factorial into z minus 1 all square plus 1 by 3 factorial into z minus 1. Next term z minus 1 all raised to 4. Z minus 1 all raised to 4 cancel those 1 by 4 factorial. And next term z minus 1 all raised to 5. So z minus 1 is in the numerator, denominator cancel. So z minus 1 by there is 5 factorial. And next term z minus 1 all square by 6 factorial, etc. So negative powers of z minus 1. Let's find the negative powers 1, 2, 3, 4. So z is equal to 1 is a pole of order 4. Then we get it here. So z equal to 1 is a pole of order 4, clearly from Lorentz series expansion also. Next function is f of z is equal to cot pi z divided by z minus a all square. We can write cot pi z as cos pi z divided by sin pi z, and there is 1 by z minus a all square in the denominator. So clearly sin and cos are different zeros, no common zeros. So this is f of z as singularity when this denominator equal to 0. When the denominator equal to 0, this is equal to 0 when z is equal to a, and sin pi z equal to 0 when z is equal to integer values and belongs to z, integer z. If z is equal to integers, that means sin pi, sin 2 pi, sin 3 pi. Also for z equal to 0, that is sin 0, sin minus pi, sin minus 2 pi. These all are 0. That means sin z is equal to 0 when z equal to n pi and belongs to integer z. So sin pi 1z, 2z, 3z, minus z, minus pi, minus 2 pi, these are 0. That means z is equal to n is the 0 of sin pi z. So here we have z equal to a and z equal to n. So singularity of these functions are z equal to a and z equal to n for n belongs to integer z. So all integers and also z equal to a. Z equal to a is any number. If it is an integer and it belongs to the singularity, or if it is any other, sometimes it is a rational number. If it is 1 by 2, it is a z minus 1 by 2 also, say equal to 1 by 2. It is a rational number or an integer. These are singularities. Now let's find what is nature. So putting z equal to a, we get cos pi a. Denominator is 0. That is 1 by 0 or any number, finite number divided by 0 is infinity. If a is not a multiple, that means a equal to 1 by 2, 3 by 2, 5 by 2, this is, if a equal to 1 by 2, 3 by 2, 5 by 2, 7 by 2, etc. That means a is 2 and plus 1 by 2. Then cos also 0, numerator also 0. So this is 0 by 0 form and pole becomes symbol pole. Or it is a pole and order 2. Since if cos pi z is not equal to 0, cos pi z not equal to 0 for z equal to a, and denominator has z equal to a as 0 and it is of 2 times. That means its derivative also 0. So pole of order 2. If cos pi z equal to 0 for z equal to a, then it will become pole of order 1. So it is symbol pole if numerator equal to 0 when z equal to a. Otherwise it is pole of order 2. That means if a is a rational number, 1 by 2, 3 by 2, 5 by 2, 7 by 2, 9 by 2, these type of 2n plus 1 by 2, then cos also becomes 0. Then it is symbol pole, otherwise it is pole of order 2. Now let's find the order of z equal to n. Z equal to n, clearly z equal to n is pole. When we put limit z tends to n f of z, cos pi n and sin pi n or n pi z n minus a all square. This is not equal to 0. This a is not an, when n is a is not an integer. Sin pi n is 0 for n is integer. Cos pi n not equal to 0 for an integer. So clearly this is cos pi n, a finite number. Cos pi n is any finite number between minus 1 to 1 and denominator is 0. This is infinity. So pole, and it is symbol pole since it is only 0 for denominator. Only the 0 of denominator. Cos and sin doesn't have any common 0. So this is a 0 of denominator. So these are symbol poles. Z equal to n are symbol poles. So cot pi z by z minus a all square has poles. Singularities are poles. For z equal to a, if numerator doesn't have 0, that means if a is not in the form 2n plus 1 pi by 2, then numerator does not 0 for the value when z equal to a, and denominator is 0, 2 times 0, so pole of order 2. Otherwise it is pole of order 1 when a equal to 1 by 2, 3 by 2, 5 by 2, numerator also 0. And the 0 of sin pi z are z equal to n, these are symbol poles. So nature of these singularities are poles. Clearly this function has poles. It is z equal to a and also for integer z.